Okay, at the last lecture I spent some time describing the UOE process and the process of making helical pipes, where you take a strip of steel and you form it into the shape of a pipe and then you weld it together. So those types of pipe, which are very common, very widely used, have longitudinal or helical spiral welds in the actual tube itself. But it would be nice to have a section of pipe which has no welds in it, and the only welds are those that join those sections together. And that's the principle behind seamless pipe. So in a seamless pipe manufacturing process, we're taking a solid block of steel and we're pressing a tool into that block of steel and forcing it through the middle of the block to turn the solid block into a tube. And that's the basic principle of the process. Of course, it's not that easy. You have to do lots of steps on the way, but it does give you the possibility of making weld-free pipe sections. So you start off generally with a round billet, and you can't plastically deform a material to make a seamless pipe at room temperature. You have to heat it up to a very high temperature. So there's a rotary heating furnace usually that's used where a cold billet is put in, and then the table rotates a bit, and then another billet is put in and it rotates a bit. And by the time you've completely filled that furnace with cold initially billets, the one that comes out is hot, and hot enough to be able to put through the process. And then you have a tool, you can see here, which you force through the middle of that billet. And you have a couple of rollers here which drive the billet onto that tool. You don't do that as a single process generally. You try to put the tool through, and then you try to stretch the tool, stretch the seamless pipe and thin the wall down with an elongator. And then you have something for making sure that the internal diameters are correct and that everything is centralized, and then some way of actually pulling the system out, and then reheat, and then you'll have some sort of sizing process. So these rollers are set at a certain size to fix the outside diameter. By this time, because this material is quite hot, it's easy to plastically deform. yield stress and the ultimate stress of materials drop as the temperature goes up. So you're trying to do this all in the plastic state. So these pipes probably have mechanical properties a bit similar to butter at these sorts of temperatures. Maybe a bit like butter that's come out of the fridge, but it's still pretty soft and easy to deform. And then when they're cooled, then you have the final good properties. During the cooling, you'll get sometimes residual stresses that vary from one side of the pipe to another, and the pipes on the cooling table will bend. So you put it through another set of rollers to straighten it, and then you do all the testing and inspection, very similar to what we've done in previous processes. You'll notice here there's a heat treatment stage as well. You may need to heat treat the whole pipe to deliver the right mechanical properties because it's been heated to a high temperature. So what you can see here with this roller is that the roller is squeezing the pipe a little bit. The tool here is fixed, and then this is being dragged forward by the geometry of the rollers and flowing over this tool. So you've got this solid sort of billet, or the solid or the thicker wall tube on this side, and you're making it into a thinner wall tube by dragging it past this tool set. So the elongator really takes this smaller diameter thick wall tube and makes it into a larger diameter thin wall tube. And you can do that several times in order to get the right size. And if you do it in small steps, you're more likely to get a good quality pipe. Because one of the big problems with seamless pipe is this might not be exactly in the middle. So that the hole in the tube isn't exactly in the middle of the tube. You get a thin wall on one side and a thick wall on another side. And in the past, it was that sort of variation in wall thickness which was the big problem that had to be dealt with. And you can understand that because you've got this very thin rod with this elongator on. It could do this quite easily inside the tool. So that's why you would get these problems. As the designs have improved and the stiffness of that rod has increased, those problems have become less. So let's look at some of these processes in a bit more detail. This is the Mannesmann plug mill process. It's almost identical to the one that I showed you before. In fact, it is identical. It's the same process. Let's look at some of these elements. First of all, you've got these forging or plug mills. So you can imagine you've got a roller here, and the roller might have some geometry. So this part of the roller's got a narrow gap, and this part's got a wide gap. You can imagine that moving along something, so there's a central filler here, and it's rolling along and it's squeezing this material, but it doesn't go the full length. You let off the pressure when this part here is rotated. And so you're thinning down this tube, and this tube is getting longer while you're doing it. So the billets are often shorter than the final tube length. So you can see it under these points here. We're rolling along, we're definitely in this range here, where we can get a thin tube. But by the time we get to the end, this part here is engaging there, and there'll be a part of the tube near the support which is not actually being thinned down. And you sometimes need to have something to hold. You can imagine then turning that around and then treating this part of the tube. So there are processes where you can do part of the tube in one point and then you rotate it and do the other part in the second stage. So you have all of these issues. Now this only works once the thing's been pierced. So the plug has got to have gone all the way through. You've got a tube already. This is reducing the wall thickness of the tube and elongating it. So here's a plug mill. I defy you to see anything in that. That's one of the billets that's being loaded into the mill. So it's going off in that direction. So this we haven't actually pierced yet. This is one of the stages. And everything else, I can't get a camera in, so I can't show you that, unfortunately. But you see the hot billet going in. That's about the limit of what you see on a lot of these processes when you wander around the plant. Unless you're there as a maintenance engineer stripping it down afterwards and finding out what happened when it went wrong, you don't tend to see very much. One of the things about these plug mills is there's a lot of surface handling. There's a lot of gripping by rollers that is required. And that means that you can get defects from that. And a very common defect is what's called this surface lap defect here. So you imagine there was a bit of metal sticking up and the roller has squashed it flat, but it hasn't squashed it enough to join things up. So you get what looks like a crack. And if you put stress on that, of course, that will act as a crack. The advantage with that is they're quite easy to find. This is a magnetic particle inspection of the surface, very simple process, and these are those surface laps here. And what it usually means is where the edges of the rollers have gripped something, you've dug in a little bit and you've pushed a little bit of material up, and then you've squashed it flat with the next roller, and that creates these laps. So again, you want to make sure that everything's lined up properly to avoid these problems with the system. So a good seamless pipe mill won't have very many surface lap defects. You can get lamination. So one of these surface laps can actually run during the process into the material, because what you're doing is connecting up the inclusions in the pipe. Now these are not rolled plates, so there's not lines of inclusions, but there still are the odd inclusion in the plate or in the billet that was being used. And the pipe, when the crack runs through it, it will find the path of least resistance, so it will tend to jump from one inclusion to another because that's a slightly lower energy process. But this is a ductile crack, really. It isn't associated with the defects. It starts from the surface and it just runs in quite some distance. Now that's obvious. If you see that, you know that you've got a bad pipe and you just reject it. It's not straightforward. It was very straightforward to see. That's another surface lap picture. If you wander around the pipe dump in many process companies that make pipe for the industry, there will be all sorts of failed things. So this is a classic surface lap. It started with a surface lap here, and then the cracks run in, and then this has been peeled off effectively. So we get this vertical crack around the edge and then this angled crack at the start. And you can see that's on the outside. Visual inspection from about 3 or 4 feet away or 3 or 4 meters away, you'll see that type of thing. So it's quite common, and it's easy to reject the pipes because of that. And one of the reasons that seamless pipe got bad reputation a few years ago was because there were too many of these types of surface laps. Not all defects, though, are due to the material manufacturing process. Some of them are due to stupidity. So this is a defect that was found on a piece of pipe that came from a mill that should have known better. And this is a lifting shackle. So they were craning the pipe segments off onto the back of a lorry. And somebody left on the pallet a shackle. And then that shackle ended up going in through the billet heater, and somebody squashed the shackle onto the surface of the pipe, and then it went through the whole process. So it actually was pushed into the surface. And the interesting thing about this one was the guy who was running the plant, who was a classic manager, all about throughput and cost and not very much about technical performance. He didn't understand the technical side, could not understand what this defect could possibly have been caused by. He did not understand the process at all. Whereas every single person on the process line, every single person on the production line knew exactly what the cause was, including the most junior member of the staff. And the indication is therefore that if you want to understand the process as a manager, you have to walk through the process and talk to all the staff and understand it, and have the same level of understanding as the most junior person in the system. Now, you don't have to understand why the process works, but you should know what you do. And you should know that pipes need to be lifted, and you should know the lifting requires shackles, and the shackles therefore must be controlled. If you don't know that, then you don't know enough about your process, and you're not going to be a very successful manager in those process situations. I just happened to see that picture, and I've got the story from the guy who did it. It's quite interesting. So seamless pipe was originally used for all small diameter high pressure pipe because we wanted to avoid the welds. High frequency welded pipe, I think, is starting to take over from seamless because it can be made more reliably with higher strength. Older seamless pipe was typified by a variation in wall thickness, as I said, because the plunger that was making the initial hole didn't go down the middle of the tube. And that gave you differences of thickness around the circumference, and it also, because of the lack of control of the rollers forcing the material around, meant that you had a lot of surface laps and surface defects. I have to say the important word in that sentence is older. Modern seamless pipe has got very good quality. Some pipe mills are better than others, but a good seamless pipe from a good pipe mill is as good as any other pipe that you're going to get. Trouble is, when you're looking at assets that are already in existence, they may have older seamless pipe systems. And if they've got older seamless pipe systems, they may have some of these defects. So if you're going to repair an older asset with old seamless pipes, you might have lamination problems, which don't occur with the newer systems. Now, we don't have generally a rolled plate microstructure. We heat this billet up to a high temperature. It's then processed at the high temperature. Most of the inclusions stay round. Most of the grains stay what we call equiaxed, which is approximately round. And that means this pipe generally has quite good resistance to hydrogen-induced cracking, because we don't have these elongated defect structures which can act as crack nuclei and can make the cracking easier. So again, in applications where we're looking at high hydrogen induced cracking probabilities, sort of wet gas environments, seamless pipes have been used preferentially before a drying stage, for instance. So next process is electrical resistance welding, or high frequency induction welding, or high frequency pipe, sometimes it's called. And this is another process where we start off with a strip. Usually a hot rolled coil is delivered. So you just get a coil of steel. And the coils can be quite big. You then have to unroll that coil and straighten out the coil and trim the edges, because you want them to be perfect. When you actually make it into a tube, they've got to line up perfectly. So there's a lot of stuff that's there to do that. And these rollers are driven at different speeds. These ones are slow, these ones are faster. So we stretch the material and get rid of the wrinkles a little bit in this stage. Then we put it through a set of shaped rollers. This is rounded, and these ones are slightly less rounded. And so you turn the strip into effectively a tube. So you're just doing that basically. Once it's sort of set, these edges are pushed together, then we have a welding stage. And that welding stage is of different types. We can have high frequency induction systems or electrical resistance systems. that different welding processes, the rest of the line would look pretty much the same. After the welding stage, there's often a trimming of the excess flash. So if you push two materials together and then heat them up so they melt, and you squeeze it, some of that molten metal will come out up and below. Because we're squeezing it to maintain the shape, we tend to get the weld metal sticking up and sticking down into the pipe much more, and we have to trim those off with a simple cutting tool. Otherwise, if a pig was going down this pipe, it would stop when it got to the weld. The weld metal is heated up and has lost its mechanical properties compared to the coil. So you might have some annealing and cooling processes that just go along the weld. So we're not heating up the whole pipe, just the weld region. So we've got a tube. Now the tube goes through a sizing set of rollers, cut-off rollers, straighten rollers, pipe end finish, hydro testing, all the sort of things that every pipe manufacturer would need to do. And there's the coating and inspection stages afterwards. So that's a coil of strip. And you can see there immediately one of the problems of dealing with a hot rolled coil of strip. They're sitting there in the open air, rusting away merrily while you wait to use them. And the pipe mills don't work on just in time in quite the same way that the car manufacturers do, for instance. So these strips can sit there for quite some time. Now they will have been corrosion protected by the steel supplier. They will have been phosphate treated and they will have been milled, but you cannot stop them from rusting, particularly where they contact the supports and things at the bottom. So you're going to get bits of rust, bits of dents. You can see here, there's a dent, and there's here a dent. There are all these wrinkles that are introduced. This is a material that you've got to handle, and you've got to deal with all of these issues that have been from the storage and manufacture. I don't know if you can see it here. There's some discoloration, rust on the outside there. Each coil is slightly different. So there's usually a cleaning stage, which I didn't put on that picture, where people try to remove these things. You have an accumulator for the strip. And if you can see it here, there's a strip that's going round here. It's like a clock spring in a spiral. And then that is effectively where you've uncoiled that coil and you've wound it on a large spool ready to be taken off down here and stretched. And those are the rollers that are stretching and the trimming operations before you go into the welding operations at the end. So because you have to deal with a whole coil, if you uncoiled the whole coil, you'd have a very, very long production line. You can reduce the length of that production line by winding it into a fairly open spiral in these cases. And you can join different strips together in that stage and accumulate it while you're making the pipe. So you could make continuous runs of pipe. And this is exactly the same if you're making copper pipe for water tubes, for the radiators that you have in here. You accumulate a lot of material and you continuously join sections together, and then that goes through the process of joining. And you could make a kilometre long tube if you wanted to by this process. What you do with it afterwards, that's a difficult thing to say, but in principle you can make continuous lengths that are very long. So this is the electrical resistance welding process. So you have a couple of squeeze rollers that squeeze these materials together. So you can see out here the materials haven't been quite squeezed together, and the electrical contacts slide on the surface where things haven't quite been squeezed together. This final set of squeeze rolls makes those surfaces come into contact. So the current flows along until it can bridge this gap and back again. And where it crosses the gap, there's a bit of contact resistance, it doubles the effective resistance. So there's more heating at that contact than there is elsewhere in the system. There's a high frequency, so the current is alternating, flowing in one direction and then in the other. And if we keep the frequency very high, the surface is where most of the current flows. The higher the frequency, the thinner the layer on the surface that current flows on. And so you want to heat the surfaces up in the welding process, so going to high frequency is a good thing to do. Now this one has sliding contacts, and obviously you've got to make sure that the electrical contacts are maintained very well. And that's why it's in electrical resistance welding. It's requiring just these sliding contacts to work, and the power supply that you've got. You can also have a big induction coil here, which is non-contact. So you wind a big coil around the outside, and then you have an alternating current in that coil. That produces a magnetic field which grows and then goes smaller, grows and then gets smaller. Alternating magnetic field then induces eddy currents in the actual surface of the pipe, and those induced currents cause the resistance heating, I²R resistance heating of the surface. Now you can see in this design, we've got those curved rollers to hold things in shape, as I was talking about before, but there's a couple of extra shaped pressure rollers just to make sure that you really are sticking those things together. And again, the eddy currents are flowing along here and back, and the actual welding process is taken at the interface between these two where they squeeze together, because the contact resistance is higher at that point. So the big problem with this process is getting it set up. Once it's set up and working, you keep it going continuously. It runs for weeks and weeks and weeks, but it might take you the best part of a week to get it all set up and everything tweaked so that everything's in the right orientation. Certainly people making water pipe, whenever they stop the process, it takes them days to get it up and running again. So they don't want the process to stop. So high reliability processes, as many extra systems like extra wheels, extra pressure systems, monitoring systems that they can put on the line to make sure it keeps running. That's what they will do. The orders for gas pipes tend to be finite. We've got a certain distance of pipe that we need to supply, so they don't run for quite such great lengths of time. Therefore, there's a lot more stop-start in the process. It's just the economics of the process. You're selling a gas pipe for a lot more than you're selling copper water pipe for your central heating system. This is, again, if you went into a modern pipe, you might see something a little bit more a little bit more advanced looking at this. But automation in this process is very important. This is an early automation system. There's a white line down the side of the pipe, which is at 90 degrees to the weld. And that white line might move around a little bit. The weld might move around a little bit because you've got different residual stresses in the pipe, slightly different alignments for different sets of coils, whatever. So all this does is this line is painted a fixed distance from one edge, which is 90 degrees apart. The sensors detect that line and they will move around the pipe, the equipment on the top, so that it follows the centre line of the weld. Just to take into consideration those variations. And this is true for heat treatment, and this is true for lining up the weld in the first place. Obviously, if you're going to have a welding station and you've got those squeeze rollers, you want the weld seam to be right between the squeeze rollers, not to run under one squeeze roller then under the other one and move around. So there's a whole sort of motion there. And those rollers can be adjusted and the pipe can be twisted to make sure that that happens correctly within a small range. It's not something that you can take a 90-degree change. So that's improved the quality of the system quite dramatically. And then what you have to do after you've made that weld is you have to heat treat the weld region to make its properties similar to the rest of the pipe. So what we have generally, if you look at the the weld itself, which is down here in the middle, and then the metal either side of it. You can see the rolled microstructure here with the directionality, and the weld which hasn't got directionality at all. You might see some slight directionality due to the cooling process and the weld freezing in the direction of maximum temperature gradient towards the middle of the weld. What you'll also see is these have very small grains, and there's some larger grains in here. So the weld hasn't got as good properties as the strip. So what you want to do is try and heat treat the weld to give it similar properties to the strip and better strength. Otherwise, if you pressurise this pipe, the weld will blow and the rest will be the same, and you don't want that to happen. So what you do is you heat the system and then spray water on to quench it, and then heat it again and allow it to cool in air normally. So we call that local double normalising with an intermediate water quench. So normalising is the process of annealing that the steelmakers use, and it's normally what's supplied to you, hence the name normalising. And what they do is they heat the surface of the steel up to about 900 degrees C, and the bulk temperature gets to about 850, 900. And then they allow it to cool in air. And that gives you a relatively small grain size of the standard thermodynamically stable structure of that steel, so ferrite and perlite. So what we're trying to do is make the structure of the weld look like a normalised steel, which is what the structure of the pipe is close to. And that's what that process does. And this is the point here. You want a similar microstructure to the parent plate, so that the weld isn't anything special. It's got the same microstructure, the same mechanical properties as the rest of the plate. And you're only heat treating the weld, and therefore you need that alignment system to make sure you're only heat treating the weld and not the parent plate. So we have a linear inductor along the top. Yeah.
When you're treating the weld, does it mean the temperature will not go through?
Yeah, the heat is just focused on that weld line. So if the weld is lined like this, you have an inductor that's lined like this, and it just heats up the weld region. And then you have to line that up along the process direction. So if you do it correctly, the rest of the pipe stays cold. It doesn't actually stay cold, but the heat on the weld takes you into this high temperature 900 degrees C range, but the rest of the weld, the rest of the material is only a few hundred degrees C.
And the microstructure of the material will not change?
Will not change. If we can keep the temperature below about 700 degrees C, the microstructure doesn't change in the time that we've got this process to run, because it's running in a few minutes. If you held the material at 700 degrees C or 600 degrees C for many hours, then it would change. The perlite would become spheroidized. But we never do that. There is no economic process that requires holding something for a long time at 600 degrees C. So you wouldn't see that. So within the time of this process, which is a few minutes, the rest of the material's microstructure does not change. And you try to adjust the inductor shape and the heating so that it's just along the weld line, and it heat the weld and the heat affected zone either side of the weld. So this is the inspection system for that. So what we've got here is a set of ultrasonic probes, an example there, and they're lined at different positions, and this roller system which rolls along the pipe, you can see there's a guideline here. This is actually going along, and those sensors are they operate at different angles. You can see an angled one there, so we can measure different depths within the system. So when we talk about ultrasonics, I'll explain this in a little bit more detail. What you're looking for is lack of fusion defects, and you calibrate therefore a notch or a depth crack in the system, and then you compare your ultrasonic responses to what you get from that calibration to know if you've got any of these things. So these are the sorts of patterns of ultrasonic waves. So you've got multi-element systems here, and they produce at different angles these things which then spiral around the pipe. And a little bit later, you pick up the pulse. So this is like a pulse echo method. You put a pulse out, it goes around the pipe, comes back up here, and is picked up at that point. And that's where you have to calibrate it very carefully. And it's based upon a moving ultrasonic array along the pipe. It's not a fixed system. This helical scan pattern is very useful because it can be set up in a very precisely in a factory situation. It's not something you would want to do on the field or on a lay barge or anything else like that, but you can use that as a very simple way to check. Because you're really only looking at what's happened along one line, along the top here. And by the helical method, you're getting different angles, which will give you different information at different points along the surface, and you can depth scan the defects, which is what you need for lamination and for lack of fusion defects. And that's what you're trying to avoid. That's a lack of fusion defect. That's an obvious one. So on the outside of the pipe, what looks like a good weld. On the inside of the pipe, you've got nothing. That particular one would fail the hydro test at about 20% of the maximum pressure that you'd expect. And you don't want that to happen. Now you might argue that if we inspected the inside of the pipe, we'd see that. But it's much more easy to look at the outside than it is the inside. And if that's in the middle of a 10-metre section of pipe, then you probably wouldn't see it unless you did the ultrasonic inspection. What's that been caused by? That's the pipe coming together and the ends, which are at 90 degrees to each other, 90 degrees, the ends come together, but the bottoms don't come together. So we haven't squared off the ends quite right. There are other defects. The flash is well trimmed on the outside because you can see it, but the flash has not been trimmed very well on the inside of the pipe. Again, because you're not going in there and having a look. And you can pick those sorts of things up in analysis afterwards. Hook cracks, hydrogen. A lot of those you can get in the pipes. This one hasn't been trimmed, you can see here, or it's been trimmed to a certain extent. That's more of a service crack. Burn marks, you see here, and here. So the post-weld heat treatment, in this case, has actually missed the weld completely. And there's been a bit here, and a bit here on either side of the weld. So you could see that, you possibly, when you looked at it, you get discoloration of the surface of the tube over off the edge. Now this one, because it's on both sides, and there looks like a little bit of a burn here on the weld. It looks like that inductor or induction system has been broken, and so you're getting more general surface heating. You're not getting it focused along the weld, and certainly it's not penetrating enough to get the weld heat treatment correct. And that would be really interpreted as lack of post-weld heat treatment because it didn't work. The process was there, it was used, but it didn't work for whatever reason. This one, the post-weld heat treating did work, but you didn't trim the flash. So now in that cross-section, you can see that the microstructure's very much the same all the way through here, so that's worked, but you've still got the flash at the bottom. So you can have combinations of defects, and they don't have to be the same combination in every failure. Pre-1970, electrical resistance welding was notorious for lack of fusion defects. And often that was because of uneven heating, and that was associated with poor fit-up and poor alignment of all of the heating elements in the system. So resistance sliders which came out of contact or which were sliding from one side of the weld to another because the weld seam was moving a little bit, all of these sorts of control issues. When you force things together, you want to squeeze out some of the molten metal, because what that molten metal does is it drags the oxide contamination out with it. And we call that upsetting the material. Doesn't mean making it cry, it means actually plastically deforming the material so that we get that flash. And that takes away some of the rust and the other defects. If you don't, therefore, force the sides together strongly enough, you don't get very much upset. You get trapped oxides in the weld at poor strength. Inspection was a problem because, as I say, the weld seam moves around a little bit, and the inspection in the early systems was fixed where they thought the middle of the weld seam would be, and the weld seam would just wander in and out of the inspection zone. It wasn't surprising that you missed defects under that case. Low toughness of the welds usually meant that the heat treatment wasn't very good, and that had to be optimised. And then you get a few problems with pressure reversals where you get plastic deformation occurring under pressure, which causes changes of the mechanical properties due to work hardening. And then over pressure cycles, you would point things more towards failure in the local regions that were slightly softer than the rest. So again, that's associated with weld mechanical properties not being very good. So this is an example of that. So you've got your internal pressure in the pipe, and you've got the diameter to thickness, depth to wall thickness ratio, the depth of the floor. If you've got a little crack or a little lack of fusion defect, divided by the wall thickness. So when we get to 1, the pipe is going to fail because the defect's all the way through the thickness. If you've got a defect in the system that reduces the wall thickness by a certain amount, then it's going to reduce the maximum pressure that you can put on the material before failure occurs. And we have a curve that goes like this, and you can prove that by just simply applying Barlow's formula in most cases, reducing the pipe wall thickness by the size of the defect. So if you imagine a pressure cycle, we increase the pressure, and then there's a region here close to the pressure limit where some plastic deformation might occur, or the defect that you've put in can grow longer. We can get ductile cracking. So suppose you put the pressure in, and the pressure is enough to open up these defects and make them get a little bit bigger. So the pressure goes here, and then when you come down for the next cycle, the defects got bigger, and therefore the failure chance has got smaller. So we go up to the second cycle here, same cycle as the first cycle, but now we get onto the failure line. So because in the first pressure cycle, we've taken it so close to the limit that we've grown the defects that you've got there, in the second cycle it's going to fail. And that's these pressure reversal failures. Big problem with old electrically resistance welded pipe, because you had these lack of fusion defects present in many cases, which you couldn't avoid. And it wasn't until the processes were very well set up that we went away from that. So since 1970, what have we done? Well, we've gone for much higher frequency resistance welding, so the frequencies have gone up, there's much more surface heating. We've gone for induction heating, which doesn't rely on these sliders, which means that the reliability of the heating process has improved. The steel has improved, lower sulfur content steels, less inclusions. You get fewer hook cracks if there's hydrogen around, because again the steel inclusions have been reduced. Better inspection, especially lining that inspection technology with the weld. And you've got better heat treatment. And again, better tracking of the weld has been a good part of that. What about corrosion-resistant alloys? Well, in principle, you can use seamless and UOE processes, maybe with slightly different welding technologies. So submerged arc welding we've used before, but you could use MIG and TIG welding, gas metal arc welding, and gas tungsten arc welding. Electron beam welding, EBW, or even laser welding for the seams. So when you've got corrosion-resistant alloys, you sometimes have to change the basic welding processes, but otherwise the rest of the technology looks very similar. But the big thing is the diameters and quantities that you are handling are usually smaller because the alloy costs so much. Yeah, that's right. Yeah, yeah. So it's not that we can't make stainless steel pipes by any of these processes, it's that we can't afford to make them. If you do get corrosion-resistant alloy pipes, though, another problem that you have to look at is handling. So this is a duplex stainless steel pipe. It's for a chemical plant. And it's been picked up by a forklift truck with a carbon steel skid. And so we've got carbon steel, which is deposited onto the surface of the stainless steel. And then we get a galvanic cell set up, and then you get rusting of the steel, and it will penetrate in that case. So if you're working with stainless steel, you use stainless steel tools, and you don't use carbon steel for anything else in the handling, if you want to get the best performance. What you'd normally do, though, is have clad or lined pipe, where you have a carbon steel outer with a corrosion-resistant alloy inner, which is usually a few millimeters thick. And what you do is you take the steel strip, and you take the corrosion-resistant alloy strip, and you'd roll them together into a single combined strip, metallurgically bonded, and then you fold them up to make the pipe. That's the usual way. And you can make pipes also by putting one cylinder inside another cylinder, and you can put them through a plug mill and expand it up to the right size, or a mandrel mill, or even in some cases an extrusion press. So you can make seamless clad pipe as well, but you start off with a tube in a tube. You don't start off with a billet. And a clad pipe, as I say, you can stack up sheets of steel, the corrosion-resistant alloys in here, some spacers. You put it through a plate mill, and then you've got two, one on the top, one on the bottom, sections where you get the corrosion-resistant alloy on top of the main alloy. And then you can press bend, or you can UOE that to make the pipe. But what you've got to do, of course, is weld now two different materials. So you may have a different process for internal welding, which is the process for the corrosion-resistant alloy, and the external welding, which is the process for mild steel. And somewhere in between the two, you've got to make sure that they're compatible with each other. So generally, you drive it by the corrosion-resistant alloy weld. You will get what's called dilution. Some of the carbon steel will migrate into that weld. So maybe its corrosion resistance isn't good, and you'd have to therefore choose your welding process in order to maximise the corrosion resistance that we've got. What do I mean by metallurgically bonded? Well, there's a clad layer, there's the base metal, there's no holes or defects along that interface. We've squashed the two materials together so that they've flown, there's no air gaps or anything else, it's perfect one-to-one gap, and that's what you really need. And I shall finish with this slide here. One thing you can do for very short lengths of pipe is just to put a corrosion-resistant alloy liner inside the pipe. So if you've got a tube of the corrosion-resistant alloy and a tube of the pipe material, if you can slot it in, then that may be good enough. You maybe don't need to weld the two together. Maybe you can actually get that welding process to take place just by heating up or pressure expanding the inner tube until it goes onto the outside. And this is often the cheapest way of making it if the pipe runs are sort of this long. If you've got an 18-metre pipe run, it's very difficult to insert the corrosion-resistant alloy tube. But for a 1 or 2 metre pipe run, that's quite possible. So there's lots of things you can do. So what I'm trying to say with this is that the processes that are used here can be used across a range of different materials. You have different setup conditions for them. But you can make seamless pipe with every alloy that is used in pipe manufacture. You can make resistance welded pipe with every alloy. It's more difficult with stainless steel, but it can be done. The welding conditions are not the same, and the cost is the main driver for choosing those processes. So it's rare that anybody would use a seamless pipe that couldn't be made by this tube insertion method, because it would be so expensive to set up something for a corrosion-resistant alloy, and the volume of corrosion-resistant alloy you need is large, so the expense is very high. So generally cost drives everything, and if you can get away with a plain carbon steel with whatever thickness allowance or whatever you want to make, that's the best way to do things. So next lecture I want to finish off pipe manufacture, and we'll talk about actually how you make a pipeline. We'll also talk before that about fittings, because they're not quite the same as the pipe material. So that's what's coming up.